In our previous class, we have discussed the reaction orders, and the reaction order may be a zero order reaction, first order reaction, second order reaction, third order reaction, and so on. But these things are very important. These units you need to remember. Okay, so for a zero order reaction, because the reaction is dependent upon actually the unit will be either you call it molar or mole per second, or in a simpler term, you sometimes may find it like mole per liter per second. For simplicity, they are written like capital M, which is equivalent to mole per liter actually. Okay. If the reaction is first order reaction, then the unit will be per second. If a reaction is second order, now these units will reverse actually. So it is actually called per mole per second. So we know capital M is representing the mole per liter. So this is actually reverse. So mole per liter will become liter per mole. So this liter will be positive value, and mole will be actually having an inverse sign here, -1, and this is second -1. So obviously this is written as because this is inverse. So you can write simply, you can remove this also, and you may write it like this. So I'm writing it here. So this is actually capital M -1 per mole per second. M-1 second. So this is S actually, so badly I put this. So this is S, and this is also having a -1 sign because this is inverse. Now you can remove this value, and actually I have written the same thing in this format. Okay. And if the reaction order now increases, now there is a power will start coming over this actually. So for a second order reaction, this is like per mole per second. Then it will become like per mole square per second for a third order reaction. So for the third order reaction, you will write second here. For fourth order reaction, you will write 3 here, and so on. So it is simply maybe written as M-2, that is per molar. So actually -2 because it is square here, S-1. Okay. So like this. And these units are really important. They are generally asked in many competitive examinations because they are. So you need to remember these values: mole per second for the zero order reaction, per second for first order reaction, per mole per second for a second order reaction, and actually it will become per mole square per second actually for a third order reaction, and so on. Now we will move to our discussion actually where we have left our. So Trishla is coming late actually. Okay, so many students are, I do not know, they are waking up or they are busy somewhere. So please come on time so that we cannot skip anything. So we have discussed these units which are very important with the in regard with these reaction orders. If there is a zero order reaction kinetics, then the unit will be mole per second. For first order reaction, this is per second. This is depending upon time only, not on the molar concentration actually. And for a second order reaction, this will be per mole per second, and so on. After this, we need to move. Oh, sorry. So now I need to share a new screen with you all, and actually we are discussing. We have left our discussion here somewhere. Actually, we are discussing this plot, which is actually called right-handed rectangular hyperbola. So this is the proper term. This is a hyperbolic curve, and this curve is representing different three sections. Actually, you can write this, and up to here, this is one, and the rest is a kind of, there is no much change, not much change in constant this velocity, and therefore you can think like this will not increase further. Sorry, this will not increase further and will remain like this. Okay, so, and even something like this. Okay, so then we'll start decreasing. Now, actually, this is called. This is called the saturation effect. This is called the saturation effect. When there is no increase, when you are increasing this, because you are increasing the substrate concentration, and the enzyme is not showing any increase in rate of reaction. So this effect is called saturation effect. Here you can assume that all the enzymes are saturated with substrate, so that all the active sites are occupied. And once the substrate is being converted into the product by one enzyme, the substrate concentration is so high that the product is released out of the enzyme, and as soon as in the microseconds, actually, the new substrate will come and bind to the same active site. Therefore, you will not seeing any, you are not observing any increase in the rate of reaction or reaction velocity. Okay, after saturation effect. Okay, so this part of this hyperbola, this is a right-handed hyperbola, or in more exact term, it is called uh, right-handed rectangular hyperbola. Okay, so this part is showing the first order reaction kinetics, because here the rate of reaction is increasing very linearly when the substrate is being added to an enzyme. And the substrate concentration is generally assumed to be more in comparison to the enzyme itself. Then it will become some kind of mixed kinetics, followed by a zero order rate kinetics. And if you were asked for the units, because this is first order reaction kinetics, so it will have a unit per second, as we have discussed recently. So per second, this is mixed kinetics. Okay, so it will not be asked like this. So this is zero order reaction kinetics. It is purely having mole per second units. Okay, so mole per second. And this, sorry, and this capital M is representing mole per liter, actually. Fine. Now, actually, I need to know this. Fine. So the enzyme substrate complex is the key to understanding this kinetic behavior. Actually, this kinetic behavior, actually, we are talking in terms of this curve, this hyperbola. So we need to understand how this is happening. To understand this, we need to understand the kinetic behavior of enzyme substrate complex. As you know, and if you read it from the Pathfinder, actually this equation is shown like this. This is a very simple equation here. So the enzyme and substrate are binding together. This enzyme will react with substrate, and before the formation of product, actually a stage that is called the enzyme substrate complex formation stage, this will happen, and this stage is followed by the formation of product. Now this product is actually the plus sign here. So the product will be released out of enzyme, and the enzyme will bind with another substrate. So this will be like this. So you can think like this enzyme will go back and then again bind with a new substrate. And actually this will take very less time. This will occur in microseconds, actually, so that this enzyme will go back and bind with new substrate, and then again this reaction will happen. Now if you closely observe this thing, this enzyme substrate complex formation is actually going to help you out to understand how this curve is coming like an hyperbola. Okay, so the formation of this enzyme substrate complex, how this is happening. Okay, so let me discuss this section from Leninger so that you can better understand this. This is a simple equation shown here, but actually this is derived from a much complex equation where you can assume like, okay, suppose there is an enzyme and there is a substrate. So this substrate is very specific for enzyme. So substrate must bind to enzyme specifically to make an enzyme substrate complex. Suppose the substrate is not very specific. Suppose this is some different relative substrate. So this can also happen that this enzyme substrate complex is broken down, is dissociated, with the reaction rate, this is actually rate constant K minus 1. If you're not able to see this, I'm zooming, I'm trying to zoom it, but it is going working fine. So suppose this is the rate constant K1 with which this reversible reaction is converting the enzyme and substrate into a complex. This can also happen if this substrate is not specific or not having so much binding affinity for the enzyme. It may be dissociated. But think of this reaction. This is a single arrow, means unidirectional reaction. Can you assume a reaction where this enzyme product complex can go back to make this enzyme substrate complex, and this enzyme substrate complex with the help of this K minus 1 will be dissociated into enzyme and substrate again. So this is actually because this is K2 for the forward reaction. So backward reaction, the rate or rate constant will be K minus 2. Because simply you can assume from here, this is K minus 1, this is K1, this is K2, this is K minus 2. So this can happen actually. This is a possibility. But actually, this is very rare possibility. Actually, to do this reaction, this is generally not happening at all. Means the probability is very, very less. So let us discuss this portion in detail to understand whether this reaction will happen and what will be the probability, so that this can again form this enzyme substrate complex. And why we are not taking this reaction into count, because this backward reaction also can happen, but we are not counting this. So there should be some reason actually. So therefore we are skipping this step. For concluding remark, actually, we have skipped this particular step, this backward reaction, because of simplicity. If we take this into account, so the equation will become very, very complex, and this will create problem for us. So therefore, for simplicity, we actually have avoided this particular backward reaction in this equation. Let me give you details of this process. Okay, so here, this enzyme substrate complex is the key to understanding this kinetic behavior. One scientist that is called Victor Henry, which is following the Wood's reaction, and you have studied Wood's reaction in chemistry. Okay, so this Victor Henry proposes in 1903 that a combination of an enzyme with a substrate molecule to form an enzyme substrate complex, and this is a necessary step in the enzymatic catalysis, because first of all you should understand that this reaction cannot happen, product cannot be formed without this particular species formation. So this enzyme substrate complex intermediate is must in enzyme catalysis, enzyme catalyzed reactions. So the second thing, so this is noted by this Victor Henry. Then this idea was expanded by these two scientists who gave this equation and this plot. One was Leonard Michaelis and second is Maud Manton in 1913. Means after about 10 years, this idea was expanded into a general theory of enzyme action. So they have formulated some equations. They have formulated and given this curve, hyperbolic curve, and so they have certain postulations. So they have postulated something. So they postulated that these two scientists, Michaelis and Manton, postulated that enzyme first combines reversibly with its substrate, that is to form the enzyme substrate complex. And actually this is relatively fast reversible step. So the first step is fast. So enzyme will very fastly bind with its substrate, and this is a fast reaction. Whereas the second reaction is a slow reaction, and we know the reaction which is the slower is going to decide the rate of reaction. Therefore, this K2 is going to decide the velocity of the reaction, or you can simple terms the kinetics of the reaction. Okay. Now, so first of all, I also actually I already told you about these steps. So they have devised two equations. In the first equation, they told that the enzyme is binding the substrate. Oh, very right. This is a fast reaction, so it will make enzyme substrate complex. Then they have given another equation that, okay, so the enzyme substrate complex is formed. Now, there is also a possibility of a reverse reaction so that the enzyme and product can form, or they can either combine to make the enzyme substrate complex again. Okay, so this is also a possibility. But this is breakdown process of this enzyme substrate complex. So here you see this equation is for the formation of enzyme substrate complex. And this step or this equation is for the breakdown of this enzyme substrate complex into the product and the enzyme. So this enzyme substrate complex then break down into the slower second step. So this step will be slower to yield the free enzyme and the reaction product P. Because the slower second reaction, this one, must limit the rate of overall reaction, and therefore this overall rate must be proportional to the concentration of the species that react in the second step, that is the enzyme substrate complex itself. So therefore from these two equations, now you are very much familiar that this reaction will not be completed until and unless, okay, so this is a complete reaction. We have combined both the equations so that we have this. So this reaction will not happen, the product formation will not take place until and unless this will not be broken down. And actually this is a slow reaction. So this will be fast and this will be slow reaction. So this is going to decide the rate of reaction. So whenever we are doing the calculations, so we will first keep into account this K2, because this is a slow reaction and this will affecting our rate kinetics. Therefore, and everything is revolving around this enzyme substrate complex. Okay, so this was Leonora Michaelis and she was Maud Manton. These two scientists said at any given time or at any given instant in an enzyme catalyzed reaction, enzyme exists in two forms. So yes, Ankita was asking this question in our last class. So, and I told you that I will come to this point, and actually this is given here. Enzyme catalyzed reaction is having enzyme, and this enzyme is present in two forms. Suppose there is an enzyme, okay. So suppose I'm writing this enzyme. So this is actually called the total enzyme, which is present in our test tube before adding the substrate into the test tube. So this is enzyme total concentration, and we have put it in the large brackets because this is showing the concentration of that particular enzyme. And T for total concentration. Now you can assume that this total concentration of enzyme is equal to two things. Means either this enzyme which is present in test tube when we added the substrate will bind with substrate to make an enzyme substrate complex, plus some of enzyme will we can assume that it will present in the test tube which is not able to bind to this particular substrate. So this is called the rest enzyme is present like this. This is the free enzyme. So this free enzyme and the enzyme which is bound with substrate is actually our total enzyme which we have taken in our test tube. This is clear? So I can remove this now. So the two forms of enzyme is the free enzyme, which is unoccupied form of enzyme, that is E itself, and the combined form, that is actually the forming the substrate complex. So this enzyme substrate complex. So now, because at a low substrate concentration, most of the enzyme present in the uncombined form, that is actually the E. But because in our calculations, in our derivations, we are taking the substrate in a very large concentration, therefore we can assume that this enzyme substrate complex is formed because the enzyme is saturated with the substrate, and the concentration of free enzyme or the uncombined enzyme is very, very low in the test tube actually. So the maximal initial rate of catalyzed reaction, that is V maximum, is observed when virtually all the enzyme is present as an enzyme substrate complex. So if you are not able to understand this line, so actually it is talking about this particular portion of this curve where this is showing first order reaction kinetics. So you can assume that at zero reaction velocity in the test tube, there is only enzyme. But if you start adding the substrate, you are increasing the concentration of substrate. Suppose you have taken a pipette and you will start adding the substrate dropwise. Now you can assume that the substrate concentration is increasing, therefore the enzyme will start binding with substrate and the rate of reaction will start increasing, okay, initially. But what will happen here? Here you can assume like this: when the enzyme and the substrate are present in equal concentration, then all the substrate have occupied the enzyme active sites, and therefore the rate of reaction will become less and less, and ultimately this is showing some saturation effect. Okay. So this is here also written, this is saturation effect. Now we're coming back to the Leninger because this is actually more information is given here. Okay, so and the second thing, will you assume that this at this condition, when this enzyme substrate complex is formed and the enzyme is saturated already, then the free enzyme, which is the unbound form of the enzyme, is vanishingly small. This is present in very small quantities in the test tube actually. So now, under these conditions, the enzyme is saturated with its substrate. So that further increase, if you increase the substrate concentration further, it is not going to affect your rate of reaction. Okay, because all the enzyme are saturated. This condition exists when the substrate is sufficiently high, that essentially all the free enzyme has been converted into the bound form, enzyme substrate complex form. So now the second thing, what will you assume? Because you are not able to see the enzyme and you are not able to see how the product is released, how the substrate is binding. So you can only assume things, certain things, before deriving an equation. So that's what exactly these two scientists have done. So after the enzyme substrate complex breakdown to yield the product, the enzyme is free for some time to catalyze the reaction of another molecule of substrate, and actually this will happen so rapidly under the saturating conditions that will not take any time. So it is actually in microseconds. The saturation effect is distinguishing characteristics of the enzyme catalyst and responsible for this plateau which is observed in this particular plot. So this plateau is actually due to this saturation effect. And this is called the saturation kinetics. Now, when an enzyme is first mixed with a large excess of substrate, suppose you have taken large excess of substrate, an enzyme is very small in comparison to that particular substrate. Now, the the statistics or the kinetics is actually called the steady state kinetics. So, okay, so let me show you something else for this so that you are able to understand better. All these things are written here, which we have already discussed. Now, okay, we will come to this portion after deriving this particular equation. So before deriving this equation, we need to do some calculations and we need to make some equations. So we will come to this and then I will tell you about these 3 points. So what is the meaning of these equations actually. Okay, but before that, actually okay, so this we have discussed. Okay, so what are the assumptions based upon which the this plot and this equation, equation or the Michaelis-Menten equation has been derived? So there are 3 assumptions. These assumptions are must before deriving the equation. Okay, so first of all, the concentration of substrate is much greater than that of the concentration of enzyme, that what we are discussing. Okay, and the second thing is the second assumption to derive this equation. What they have assumed, the rate of formation of enzyme substrate complex is equal to the breakdown of enzyme substrate complex. So this particular point is called a steady state assumption. But before achieving this steady state, we also have a pre-steady state to get the steady state actually. Okay. Now, the third assumption will remain very little accumulation of the product because the second reaction is slow. So the formation of enzyme substrate complex from the enzyme product is very negligible. Okay, so because the product will not accumulate, so the product will be released out of the enzyme, therefore the chance of backward reaction will be very negligible. Because enzyme accelerate the rate of forward reaction as well as the reverse reaction, it would be helpful to ignore any backward reaction by which enzyme product might be form the enzyme substrate complex again. However, if we observe only the initial velocity for the reaction immediately after this enzyme and substrate are mixed, in the absence of product, the rate of any backward reaction is negligible because its rate will be proportional to the product, and the product is essentially remain zero because the product will not be accumulated initially. So we can leave this particular reaction. So the backward reaction will not take place. Now, what is the steady state actually? Now there is another curve. Actually, this is a combination of four things. I will tell you what this curve is actually telling us. So suppose there in the test tube at time 0 when there is no enzyme. Okay, so this time we can assume like we have taken substrate into our test tube. So we are having a test tube. We are taking substrate into this. Okay, so at time 0 there is only substrate. Actually it is having some concentration, but when you add enzyme in this, so this is enzyme, okay, free enzyme. So this free enzyme with the increasing concentration of substrate or whatever you say, the substrate concentration will decrease and the product concentration will increase. So these two curves are showing the substrate will decrease, the product will increase with the time when you add enzyme to this particular test tube. The second thing is, okay, let we closely look this. So these two are also crossing each other. So actually this black colored line, so solid line is actually showing the concentration of free enzyme. So the free enzyme will decrease and the concentration of enzyme substrate complex will increase. And you know, in the test tube, the concentration of the total enzyme, because this total enzyme is a combination of enzyme substrate complex and the free enzyme. So therefore, it will remain constant because it is a combination or it is the addition of these two values. So only the free enzyme will decrease and the concentration of enzyme substrate complex will increase, and this will decrease. Sorry. Hope this is clear. And then we are moving. So the interpretation of the Michaelis-Menten model were refined by the Briggs and Haldane, who give this steady state assumption. I also told you in the last class, this is given by these two scientists, Briggs and Haldane, in 1925. The steady state hypothesis state that the concentration of enzyme substrate complex will remain constant. So it is telling this concentration will remain constant through much of the reaction. Most part of the reaction, this concentration will remain constant. And when the substrate is consumed, then only it will start decreasing. Okay, so the much of the reaction is showing the constant value of this intermediate. Okay, fine. So this is actually called the steady state. So in simple terms, you can show it like the change in the concentration of enzyme substrate complex with respect to time, small time, change in time, dt or delta t, that will be equal to 0. There is no change in enzyme substrate concentration in most of the reaction. Okay, so therefore that it is represented like this. The second thing is, note that this enzyme plus enzyme substrate complex is the total enzyme which is present in your test tube. So it is shown by, it can be shown like this. Fine, now we move to the Lenizer. If you are able to understand the steady state assumption, steady state is only telling us that the enzyme substrate complex will remain constant throughout most of the reaction actually. If we leave some part of the reaction initial time and if we left some part in the last of the reaction where the substrate concentration will start decreasing. Otherwise, in most of the reaction, the enzyme substrate concentration will remain constant. So this is actually called the steady state assumption. This assumption is very important in deriving the Michaelis-Menten equation. Now, when the enzyme is first mixed with the large excess of substrate, because it is our first assumption that we are taking the large excess of substrate. So the initial transient period that is called pre-steady state means It is talking about the time. Okay, so if you are not able to understand this, let me show you this. So this particular time, so this is pre-steady state, because when the steady state is reached, this enzyme substrate complex is formed, and this will remain constant for most of the reaction. So this is called pre-steady state, initial transient period of any reaction, enzyme catalyzed reaction, during which the concentration of enzyme substrate is start building up. Okay, so this can also be understood from the second plot, where the concentrations start accumulating. So suppose this enzyme substrate complexes start forming here. So this is actually the pre-steady state up to this point. Then, and actually you can see this, if this is the time of a reaction, this portion is very, very negligible. And after this, this whole time is showing this enzyme substrate concentration is almost constant, if it's not at the last, but it is almost constant. Okay. So this period, this pre-steady state is very brief, okay, in overall time of reaction, and is often too short to be easily observed. It cannot be observed. It will last for microseconds. And the reaction is quickly achieves a steady state after this microsecond period of time. Okay. And then the enzyme substrate complex concentration will remain approximately constant over time of the reaction. Okay, this concept is given by Briggs and Haltin in 1925. We have discussed this part in our last class, so you can read out this. You can read this text, but actually whatever is written, I already told you. So now this will remain constant or steady. Therefore, it is called steady state assumption, and therefore analysis of these initial rate is referred to as steady state kinetics. Now we are going to derive an equation that is called, this particular equation is called Michaelis-Menten equation, that is V naught, that is initial velocity, is equal to V maximum into substrate concentration divided by Km plus substrate concentration. To derive this particular equation, we need these assumptions which we have taken into account. These three assumptions will be very, very significant to help us derive this equation. Okay, so the concentration of substrate is very, very high when compared to enzyme. Second is steady state, means whatever the enzyme substrate concentration is remain steady for most of the reaction. And second thing is formation of enzyme substrate complex will be equal to the breakdown of this complex. Third is, this is negligible. The product will not accumulate, therefore we can ignore the backward reaction. So there is no K minus 2 rate constant in this equation. Okay. Now, these values, the substrate concentration, initial velocity, maximal velocity, and the Km is the concentration at which the reaction velocity is half V maximum. This we can measure experimentally. And once we measure them experimentally, we can put their values in this equation to get any missing value. Suppose you do not know the Km and you know the rest of the things, so you can calculate the Km and so on. So you can calculate the substrate concentration, V maximum, what is the maximum velocity of the reaction, or the initial velocity of any reaction. So if one variable is missing, you can calculate, and these values can be calculated experimentally also. So therefore, you can calculate them, you can experimentally determine them to validate your equation. Okay. And if everything is fine, your calculated value will be equal to your experimentally observed value. Therefore, you can cross check your values. So therefore, this equation is remain very, very important in all the calculation in enzyme kinetics. Okay. Now, how to derive this equation? This is a big question in today's class. Okay. So first of all, so we will take this into account. This is a steady state assumption, and the concentration of product will negligible, and therefore we make simplify assumption that reverse reaction, that is the product to substrate, which is described by K minus 2, that is a backward reaction, can be ignored. Simply we ignore this, so that our equation will become simple as shown in your Pathfinder book. Okay, so this is the final equation because we have removed the possibility of a backward reaction because this product will not accumulate. This will be released out of the enzyme as soon as it is formed. Therefore, the V naught, that is the rate, initial rate, or the breakdown of this enzyme substrate complex can be calculated like, because I also told you in the initiation of this class that this K2 is going to decide the rate of reaction. So therefore, initial rate of reaction will be equal to this rate constant into the substrate concentration. So here, this is the substrate actually. The enzyme substrate complex is the substrate for this half of reaction. So this for this reaction, when this enzyme substrate complex is broken down into the enzyme product, this will remain the rate constant. And this we have discussed how to calculate the rate of a reaction in our first class. So if you do not remember, you can go to the first page of reaction kinetics where we have started this topic, and you can easily find if you are having only one substrate. So the rate of reaction is actually this. So this is the rate. Okay, simply we have taken rate. So rate is actually the initial rate is called V0 or V naught. Then you have, it will be equal to a rate constant, which is K2 here, because this K2 is going to affect your rate of the reaction. So this is actually K2, and this substrate is actually the enzyme substrate complex. So we have taken enzyme substrate complex. So we can simply write this equation like this, and therefore, so V naught is equal to K2 into ES. If you are able to understand this from here, let's move back into the, so this V naught is equal to K2 into ES. Now this thing is very, very complex actually, this enzyme substrate complex. Therefore, you need to simplify this part of this equation and then put this value again into this equation to get the final equation that is called Michaelis-Menten equation, which is actually this one. So to derive this equation, we first simplify this enzyme substrate complex. Okay, it is not easily measured experimentally because we only know the enzyme concentration, we know the substrate concentration, we know the product is released and enzyme is uh, again free to bind with another substrate. But we do not know, we cannot measure this experimentally, how much enzyme substrate product, enzyme substrate complex is being formed, because this is an intermediate. Okay, so therefore we need to simplify this value so that we can get some good values instead of this ES. Okay, so therefore we need to find an alternative expression for this term, that is ES actually. So first of all, we introduce the term ET. We know the total enzyme concentration is a combination of enzyme substrate plus the free enzyme. We know this. If we subtract, so the total enzyme concentration will be the sum of free enzyme and substrate bound enzyme. We know this. Therefore, free or unbound enzyme E can be calculated from the if we subtract this value, this ES concentration from the total enzyme. Therefore, it will be called the free enzyme, which will remain in the solution. So the free or unbound enzyme will be equal to ET minus ES concentration. Also, because substrate is ordinarily very much higher concentration than total enzyme, therefore the amount of substrate bound to the enzyme at any given time will be negligible when compared to the substrate. So the enzyme will be negligible. This particular enzyme substrate complex which is forming, it will be negligible in comparison to the substrate concentration, total substrate concentration we are taking account. So with these conditions and keeping in mind, we are able to devise two equations. In the first equation, okay, so to divide this, actually you need to keep this equation in mind. So meanwhile, we are having an equation. So this is the equation. This enzyme and substrate is having some reversible reaction. K1 is the rate constant, K minus 1 is the backward rate constant, and this K2 is converting this ES into enzyme product. Now this is in between, this enzyme substrate complex is in between. So you can assume like there is only one reaction to make enzyme substrate complex, which is actually having rate constant K1, whereas this enzyme substrate complex is broken down two ways, either to make the product or either to release the substrate. This is having two rate constant. One is K minus 1, one is K2. So if you are having, you are keeping this equation in mind, now you can again go to this equation. So the rate of formation of enzyme substrate complex will only having one rate constant K1, okay, whereas the breakdown will have two rate constant K minus 1 and K2. So we have simplified this equation actually, and this is actually the enzyme substrate complex. So actually to calculate the free enzyme, and if you multiply the free enzyme with the substrate concentration, you will somehow get enzyme substrate concentration. Okay. So to calculate the free enzyme, we already have taken into account the total enzyme minus the enzyme substrate concentration. So it is actually equal to your free enzyme. So here you can write, actually in the first step, you can write this is actually the enzyme concentration. So this is free E, and you can put the bracket so that showing the concentration. So this enzyme concentration, which is the free enzyme, can be shown like ET minus ES. So this ET minus ES, and this is multiplied by some value that is substrate concentration. So this is your enzyme, this is your substrate. Okay, and this we need a rate constant, so the K1 will be the rate constant, because we know it is only the step 1 is governed by only K1, because this is for the formation, whereas for breakdown we are having a combination K minus 1 and K2. Okay, I need to do this. If you are not able to understand, please stop me here, I will tell it again. If you are able to understand, this is very easy actually. For the formation of this enzyme substrate complex, you are having only one reaction, and this is having a constant that is called K1, and you have two reactants, one is enzyme, one is substrate. For the enzyme, actually we have taken Et minus Es, and this is the second reactant, therefore we have multiplied with substrate. Okay, so we have substrate, this is one reactant, and we have taken the total enzyme, sorry, free enzyme concentration, and free enzyme is equal to Et minus Es, and we have put it K1 as rate constant, and this is the rate of Es formation. Similarly for breakdown, actually we are having, okay, now when we come to breakdown, so for breakdown, we are having only one reactant. This is enzyme substrate complex, and we are having two rate constant, K2 and K minus 1. In the both direction, it can be dissociated. Okay. So for breakdown, actually, we have taken two values. So K minus 1, this is the reactant, this is the substrate, which is going to break down. So this is ES here, this is the ES here again. So this is K minus 1, this is K2, and we have added both the values for the total breakdown of this enzyme substrate complex. Fine. Hope this is clear. If you are not clear, please raise a query. Then we are going to the next step. Okay, fine. I assume that you are able to understand this. Now, according to the steady state assumption, what we are saying that this formation of enzyme substrate complex will be equal to the breakdown of this. So we can put this equation equal to this equation. So what exactly we have did is K1 Et minus Es into substrate concentration will be equal to K minus 1 into Es concentration plus K2 Es. So this will become equal because the rate of formation of enzyme substrate complex will be equal to the breakdown of enzyme substrate complex. From the steady state assumption, we got this. Then the third concept is the step third in a series of steps. So we will rearrange these values. Now this equation, this particular equation, which is the 615 in this book, this is the 7th edition Leninzer. Okay, so it is given, it is not correct actually. So there is a mistake in this book. Please correct that particular mistake in this standard book. Okay, so when you rearrange these equations, now see here this K1 Et into substrate concentration, this is very clear because we have multiplied this with this. Now this is minus sign here, and if you are writing Es here, this cannot be Es because this E is a misprint here. So you will remove E from here. This is only the substrate concentration because you are multiplying the substrate concentration with this enzyme substrate complex. so that you are able to get this and you will close your bracket here. Okay, and it is equal to k minus 1 plus k2. That is very correct. We will take them in bracket, and this will be common, this enzyme substrate complex. So there is a multiplication sign. Obviously there is no sign, so there is multiplication sign. So this is correct now. And only misprinting in this particular book is there should be no enzyme E here in this particular bracket, and this bracket should be closed. Hope this you are able to understand this, and if you are able to understand this, you then correctly solve this particular equation. Now what will you do? Okay, so this k1, okay, so you are going to add this term both the sides. So this is k1, this is es into s. Actually we are getting from here. If you are not able to see it again, actually I have removed this e in the when we are talking about this term. So you are having exactly this value. So if you add this term here and here, this will be cancelled out and this will be cancelled out. What will remain? This will remain only. Okay, so this will remain like K1 ET into substrate concentration. K1 ET into substrate concentration, and you will close this particular bracket here. Okay, and on the other side you will have K minus 1 K2 ES, but you will add this term this side also. Therefore you will also have okay, first of all you will have K1 into substrate concentration S, because you will take this common. So this will become in this bracket. So this is enzyme substrate concentration, but you will have K1 into substrate concentration here. Okay, so in this bracket you will add K1 into substrate concentration plus K minus 1 and K2. So see, this is K1 into substrate concentration, K minus 1, K2, and there is an enzyme substrate concentration, and then you will close this particular. Okay, no need to close this bracket, but you need to close this bracket actually. Fine. So now, if you solve this equation, if you are able to understand up to here, now it is very, very easy actually. What will you do? You will take this on this side, and rest this portion you will move to that side, and that side it will go into division actually. So the K1 ET into S, which is this term, and this term will go into division, K1 into substrate concentration plus K minus 1 plus K2. If this will come into division, now you need to solve this out. So you will divide by K1. So you will take this, if you divide by K1, this will be cancelled out, and you will take the substrate concentration outside plus these two values K minus 1 and K2 you will take into a bracket, and you will divide by K1. Now this is solved like this. If you solve this, now from our previous discussion also we know that the Michaelis-Menten constant Km actually is known by this value. So this K minus 1 plus K2 divided by K1 is actually called the Michaelis-Menten constant, and this is represented by Km. If you are not able to understand this, I will again tell you this is K minus 1 plus K2 upon K1. So from here also this can be deduced, K minus 1 plus K2. So this is K minus 1 plus K2 divided by K1. This is very simple to write and assume, because enzyme substrate complex is broken down two ways. This is the sum of K minus 1 plus K2 divided by the formation. So for any reaction you need, we always write breakdown divided by formation constant. So the formation constant is only 1 K1, whereas the breakdown constant is 2. Weight constants are K minus 1 and K2. So K minus 1 plus K2 divided by K1 is actually called the Michaelis-Menten constant, which is the concentration at which our rate of reaction is actually half V maximum. So this is Km. This Km is coming from this particular equation only. So this is a simple reaction. Hope this is clear. Okay, so that we can move again to our. So if you are able to put a value of Km here, so this will become enzyme substrate concentration is equal to ET into substrate concentration divided by this is Km actually, so Km plus substrate concentration. Now if you look your original equation, so in original Michaelis-Menten equation they have derived actually, so this is also given here also, so you can find it out. Actually, in the final equation, they have given that V is equal to V maximum into substrate concentration, Ks, sorry, this is Km plus substrate concentration. So we are able to achieve this value, and we are also having the substrate concentration in there. We only need V maximum here. So how to get the V maximum instead of this Et? So we need to remove these two terms. Here we need V and here we need V maximum. Okay. Otherwise, everything is fine in this equation. So to get the original equation, what will we do? Now we will express, we will put this enzyme substrate value into our first equation. Very first equation was something like this. So V naught is equal to K2 into enzyme substrate concentration. If you put the enzyme substrate concentration here, you will get V naught equal to K2 into this value. So V naught is equal to will become V naught will be equal to become K2, and this is the value of this enzyme substrate complex. So Et into substrate concentration divided by Km plus substrate concentration. Finally, you know this K2 into Et is actually called the Vmax. So the maximal velocity, this equation can be further simplified because the maximal velocity, you know, when the total enzyme is having, so this when the enzyme is saturated, that is when this enzyme substrate complex is formed. So this will be our Et actually. So there is no free enzyme at all. So the enzyme total will be equal to enzyme substrate complex. Okay. Therefore, the V maximum can be defined as K2 Et, because when you are having some saturating effect, all the substrate are bound to enzyme, and then you can assume that, because we, okay, so this is quite confusing. Let me clear this one. So actually we were assuming this, no? We are saying that total enzyme concentration is equal to, oh sorry, oh, why this is coming, total enzyme concentration Et, actually this is a subscript, so I am putting like this, is equal to the free enzyme plus the enzyme substrate complex. But suppose all the enzyme is saturated, so this will form, then you can assume this enzyme, free enzyme, will be very negligible, so that you can delete this particular value. Okay, you can neglect this. Therefore this total enzyme concentration will be equal to Es. That's what he is exactly saying. This Es is equal to Et when the enzyme is saturated with uh, substrate. Therefore, the maximal velocity can be defined as K2 into Et, total enzyme concentration. So this K2 and Et can be simplified as V maximum. Therefore, this will become our Michaelis-Menten equation, where initial velocity will be equal to V maximum into substrate concentration divided by Km plus substrate concentration, which is achieved from here. So this is actually called the rate equation. Now there is three possibilities. Okay, so first of all, you can assume that this substrate concentration is less than Km, this is more than Km, or it is equal to Km. Then what can happen actually? So this is given in your Pathfinder also. So there is three possibilities if you are able to achieve this equation, where V naught, or initial velocity V, is equal to V maximum into substrate concentration Km plus substrate concentration. So there are three possibilities. First of all, the substrate concentration is very less than Km. Suppose this is the Km for your enzyme, and you are having a substrate concentration somewhere here. Okay, you are having that much of substrate only. Then what should happen? Okay, so if you assume this, then what will happen? The substrate concentration is very less than Km. So you can remove, okay, so you can remove this substrate concentration from here and from here. Okay, so this will become Km only. Okay, and the second thing is, if you are having very less substrate, If you are having very less substrate, exactly I have drawn it like this. Suppose this is your Km, and you are having substrate concentration something, only this much of substrate you have in your hand. Then you can see that this will become something like this. So this is the first order rate kinetics. Therefore, you can say that the rate of reaction is directly proportional to, because this line is very straight. So the rate of reaction is directly proportional to our substrate concentration. Therefore, you can write this like this. So then the rate of reaction, or the initial rate, that is V actually, in Lehninger this is represented by V0, that is the initial rate of reaction. V0 or V initial rate is directly proportional to the substrate concentration, because it is showing the first order rate kinetics. Okay. Now assume you are having substrate concentration very high than Km value. Then what will happen? Then suppose the second thing is, assume now you are having substrate concentration something here, that much of substrate you are having in your hand. So this Km value can be neglected, so that this substrate is very high. Therefore, you will see that your rate of reaction will become maximal here. So because this will approaching this maximum curve. Okay. Other thing, how you will calculate this from the equation. Suppose you are having very much this substrate concentration. So you can neglect this value. You can neglect the Km. If you neglect the Km, this is a plus sign here. You can easily neglect this. If you neglect this can be 0, and this is very high. Therefore, this will cancel this substrate concentration, which is which is multiplying with this V maximum. Therefore, your rate of reaction V will become equal to V maximum. So these can be asked like questions. When you are having substrate concentration very less than Km, what will happen? So the rate of reaction will become directly proportional to the substrate concentration. Same thing when you are having the substrate concentration very high than Km, what will happen? So you can assume from this equation that this will going to cancel this. So V will equal to V maximum. So your rate of reaction initial rate of reaction will become equal to the maximum rate. Okay. So actually, generally we follow this trend, but this can also happen that you are having exactly that much of substrate concentration as equal to your Km. Then what will happen? So you can replace this Km with substrate concentration. So this equation will become like, okay, let me clear these values, these equations first. Then I'm coming on third possibility. So this for third one, actually, when you are having the substrate concentration is equal to Km. So here you can assume that, okay, this Km is equal to substrate concentration. So I'm placing substrate concentration instead of Km here. So if you are having substrate concentration instead of Km, this will become 2S, and S will be cancelled by, so this will become equal to, so divided by 2S. 2S. Now this substrate concentration will cancel this substrate concentration below, so that this will become equal to V maximum divided by 2. Hope this is clear. If not, I'm trying to write it again. So this will become 2S, and this will become V maximum into substrate concentration. So you can cancel the substrate concentration by substrate concentration, so that you will only have V maximum in your hand. So this will be cancelled out by this, and you will have V maximum divided by 2. So you will have half maximal velocity. So actually we are saying it many times, then the Km is the substrate concentration at which velocity is V maximum. But someone asks you to prove this, then first of all you need to derive this equation, Michaelis-Menten equation. Then you need to tell him, assume substrate concentration is equal to Km. Then you will place these values so that this will become V maximum divided by 2. So exactly how we are able to get these values is like this. Okay, so now you can think like this velocity will be equal to half V maximum at Km value. Okay. Okay, finally we are able to derive this equation, Michaelis-Menten equation, and we are able to we also have discussed all the three possibilities, and different type of question can be asked from these possibilities. So you need to remember these values. Okay, so when the substrate concentration is less, high, or equal to Km, what can happen? Okay, and for the Km value, actually, we always say like this maximal velocity will be divided by 2 is actually the substrate concentration is known as the Michaelis constant. According to the Michaelis-Menten equation, the reaction velocity versus the substrate concentration shows the hyperbolic plot. And actually it is called the right-handed rectangular hyperbola. Michaelis and Menten noted the two significant features about the kinetics of this particular reaction. When the substrate concentration was kept constant, suppose you are having a substrate concentration, you are not going to change this. Okay, so the enzyme concentration was increased. So the rate of reaction will increase because the enzyme concentration is increasing. So the rate of reaction will increase. But suppose the enzyme concentration is kept constant, so all the enzyme will bind with substrate and this will show some kind of saturation effect. So some maximal value will be shown, that is called V maximum, and then leveled off. Then the maximal velocity will remain constant for some time and then it will start decreasing. It is caused by the saturation of all the available enzyme binding sites that are called active sites, which are present for the substrate molecules to bind. Since at very low concentration of the substrate, velocity is actually proportional to the substrate concentration. We also seen from here also. So it is actually something. So from here actually we have seen that this is very proportional. Rate of reaction is proportional to the substrate concentration when the substrate concentration is low than Km. So and approaches a maximal limit, and actually it is the first order reaction at a high velocity, high substrate concentration. Velocity will become the virtually independent of substrate concentration, and this is called the zero order rate kinetics. And approach and maximal limit and Pluto like structure will form. So since the rate of no longer dependent on the substrate concentration at a high concentration of substrate, the enzyme catalyzed reaction is said to be zero order kinetics. So therefore they have seen two things. One is initially the reaction will be first order rate, showing the first order rate kinetics, first order reaction, and then it will become zero order rate reaction. Okay, so this also I have told you. Okay, so this model, which is shown by these Michaelis-Menten model, is based upon these assumptions, and actually we have also discussed these assumptions. You need to remember them. The substrate concentration is very greater than enzyme concentration. There is a steady state so that the formation of enzyme substrate complex is equal to the breakdown. And the third is the product accumulation is negligible. Therefore, there is no reverse reaction. So uh, you can remove the possibility of any reverse reaction initially. Therefore, you can derive this equation based upon this steady state kinetic model. So this kinetic model is showing the four things. First, the substrate concentration will decrease, product concentration will increase with the time. Second thing is enzyme substrate complex will start accumulating, and this is showing a pre-steady state initially for microseconds, and then it will showing the steady state. So the concentration of enzyme substrate complex will remain the constant for most of the reaction, and the free enzyme concentration will decrease as the enzyme substrate complex will increase. And one more thing is the total enzyme will remain constant because the total enzyme is a sum of the free enzyme and enzyme substrate complex formed in the reaction vessel. Okay, so you can write this. Now, what are the significance of Km and V maximum? Before starting this, if you are having any query, you please ask them so that we can start the significance of Michaelis constant and the V maximum value, which is actually we have derived from this equation. If you are having any queries, please ask, because actually I do not know how many of you are able to understand. And actually this kinetic equation, generation of this equation, Michaelis-Menten equation, and derivation of this plot from that particular equation. Okay, fine. So Likita is having no queries, and I assume that also other students are also not having any problem in this, because everything was so much simplified. Okay, so now because we have two things in our hand from the equation, and we know this equation, it is having two things. One is V maximum, one is Km value. So what is the significance of having these values in this equation? So this is a question. This question should come into our mind now. So the first thing is the Km, and the second thing is the V maximum. So Km is called the Michaelis constant, we know, and varies considerably from one enzyme to another, because there are two types of enzymes we know. One is called low Km enzyme, one is called high Km enzymes. So therefore, from enzyme to enzyme, this value is going to differ. This will vary. Also, with different substrate, for the same enzyme, the Km can vary. By definition, it is equal to the substrate concentration. Up to here, actually, we all are able to understand this Km is actually the substrate concentration. I also told you by deriving this equation, at which the rate of reaction is half V maximum, means the reaction is just half of the V maximal velocity, maximum rate. In another way, Km represent the substrate concentration at which half of the enzyme active sites are actually occupied by the substrate molecules. So in other terms, you can define in such a way that the half of the sites, half of the enzyme active sites are occupied with the substrate molecules. So you can, either way you can say this. So value of Km is sometimes equated with the dissociation constant Ks. Therefore, this value is important to know in enzyme substrate complexes. So this is true only when this K2 is very, very less than K minus 1. So that, okay, so if this is given, so you need to assume one thing first of all. So I'm leaving another equation. So see here, there was an equation when the enzyme and substrate are getting converted into enzyme substrate complex, and this complex is broken down. Now for Km to consider, you need to know this K2 should be very, very less than this particular K minus 1. So mostly, in most of the cases, this enzyme substrate complex is broken down into the enzyme and substrate again. Okay. So when you are assuming that this K2 is very, very less than K minus 1, so that this is true. So this Km is equal to K minus 1 plus K2, as I told you earlier also, K minus 1 plus K2 divided by K1. So K minus 1 plus K2 divided by K1. Now you know this K minus 1 divided by K1 and K2 divided by K1. This can be obtained. And actually this is the dissociation constant, because this K minus 1 is very, very larger than K2 value. Therefore, this can be written like Ks, that is the dissociation constant, and this will remain as such, K2 upon K1. So somewhere, sometimes you will find the Km like this, the dissociation constant plus K2 upon K1. Since this Ks is the dissociation constant of an enzyme substrate complex, if you decrease the Km, the enzyme affinity for the substrate will increase, and vice versa. If you decrease the Ks value, so that therefore the measure of how tightly the substrate is bound to the enzyme. So in simple terms, this Km is equal to Ks plus K2 upon K1. So you can think of this as directly proportional to this Ks. Okay. So if the Ks value is high, if the Ks value will decrease or the Km value will decrease, enzyme affinity for the substrate will increase. Means it is having an inverse relation. If the Km value will increase, the affinity for its substrate will decrease. Okay. So it is, so you need to underline this line. So therefore, what is the significance of Km? Km is the measure of how tightly the substrate is able to bind to its enzyme. So it will show the affinity, tightness of the binding of enzyme and substrate. If it is less, the affinity is more. If it is high, affinity is less. So it is having an inverse relationship kind of, because it is directly proportional to the dissociation constant. Okay, so the greater is the value of Km, the less tightly the substrate will bind to the enzyme. So this is having an inverse relationship, right? Km depend upon temperature, the nature of substrate, pH, ionic strength, and other reaction conditions. So this you should keep into mind. All these are going to affect the Km value, not only the enzyme and substrate, but if the temperature varies, temperature, nature of the substrate, pH value, ionic strength, and other reaction conditions, they all affect the Km value. So therefore, its value serves to characterize a particular enzyme substrate system under a specific condition. So two things it will tell: under which condition, under which specific conditions the reaction is actually happening. And the second thing is how tightly the substrate is able to bind to its enzyme. It is, if you are having Km value less, then it will bind tightly. If you are having Km value high, then it will bind less tightly. And the second thing is, because it is going to affect by various conditions, temperature, pH, and ionic strength conditions, it will also tell something about the specific conditions for any reaction. Okay. Now the second term is V maximum. So the V maximum significance is shown by either catalytic constant or the specificity constant we have discussed in our previous class. Let us quickly finish this particular topic because we already have discussed this one. So the V maximum has a well-defined meaning, both theoretically and empirically, because you are able to understand the V maximum value is some value at which all the enzyme are bound to the substrate, and the free enzyme is very, very less present in the solution. Okay. And it is the theoretically highest possible value of the rate of reaction which an enzyme can catalyze. So it represents the maximum rate which can be attainable, okay, which can be reached. That is, it is a rate at which the total enzyme concentration is present as the enzyme substrate complex is formed. Okay, so the total enzyme concentration ET is actually showing the enzyme substrate complex, and you can write like because the initial velocity you write K2 ES for the final V maximum rate of reaction you can calculate by K2 into enzyme and total enzyme concentration. So it is the total enzyme concentration actually. So this ET, K2 ET, actually we had discussed it earlier also when we are replacing this particular term K2 ET with V maximum. So you know the V maximum is equal to K2 and ET. And this ET is actually showing the enzyme substrate complex which is formed in the reaction and the enzyme is saturated. So therefore, this is something like this. Now you can calculate the catalytic constant based upon this V maximum. How? If you divide this ET, okay, if you move this ET to this side, it will coming in division. So V maximum divided by ET is actually equal to K2, and this K2 is actually called the K catalytic constant. This K2 is called the catalytic constant, and it is also shown by K cat value. Okay, so the catalytic constant is the rate of product formation in a unit time, and the unit time is generally per second. Rate of product formation when an enzyme is saturated with the substrate, Kcat, is also called a turnover number. So this turnover number is represented by either K2 or Kcat, catalytic constant. Okay. So for ease, you can calculate it from here. You need to move this ET to this side so that you can get K2. And this is called the catalytic constant or the turnover number. Turnover number of an enzyme is the number of substrate molecules converted into the product by the enzyme molecule in a unit time, which is generally per second. So unit will remain per second. You need to underline some lines, some things. So for example, catalytic constant is either represented by K2, Kcat, or the turnover number, and this is unit is actually per second. Okay. Then, okay, with the help of V maximum, you are able to calculate the catalytic constant or the turnover number, means an enzyme is able to convert how many substrate molecules in per second time. Based upon this, you can classify some of the enzymes based upon their catalytic constant. For example, catalase is having the highest value, 4 into 10 to the power 7. then followed by carbonic anhydrase and so on. So lysozyme is having only 0.5 and DNA polymerase is having some 15. So DNA polymerase 1 is having can convert 15, means it can polymerize 15 nucleotides per second. Okay, similarly chymotrypsin can convert 100, can break down 100 bonds and so on. There are many things we can assume. So the catalytic constant or turnover number we can find. Second thing is based upon this kcat value. If you divide this kcat value with the Km Michaelis constant, you will able to get one more constant that is called specificity constant. Okay, so this specificity constant is having units per mole per second. So simply what you are doing, you are dividing with this kcat value which is having per second unit with some Km value, and you know the Km is the substrate concentration, so it will have per mole per liters or capital M inverse, because this Km is dividing. So this will, if this molar or M will go, concentration will go this way, so this will become M minus 1, and the kcat is already having the unit per second, therefore it will become per mole per second. If you remember, this is the same unit for second order rate kinetics. So second order rates reactions are also having the same unit. Therefore this is called specificity constant. Specificity constant. Okay, an enzyme with high Km require the higher. I do not know. Fine. So actually I need to remove this, otherwise I cannot annotate this. Okay. So thus the ratio, this ratio kcat upon Km is actually equivalent to the rate constant for a reaction between the free enzyme and the free substrate. Therefore, this is called the specificity constant. And actually this is called the catalytic efficiency. Okay. It is a measure of catalytic efficiency, how efficiently an enzyme is able to convert the substrate into the product at a low substrate concentration. So this is called the catalytic efficiency or the specificity constant. Whereas the kcat is called the turnover number. Similarly, the specificity constant is called catalytic efficiency. So I would like to underline some points so that you can catalytic efficiency. This is also called specificity constant. And actually, it is only this part of this equations, kcat divided by km. So, okay, this is actually discussed. And it is having units of per mole per second. I also have discussed. Thus, the rate of product formation is dependent upon how well the enzyme binds to the substrate. That is actually the Km value, how well an enzyme is bound to the substrate, and how fast, that is the catalytic efficiency, how fast the enzyme converts the substrate into the product once substrate is able to bound to the enzyme. So this is actually called the catalytic efficiency. So based upon Km and V maximum, you are able to calculate turnover number, catalytic efficiency, and the affinity with which the enzyme is able to bound to the substrate, and so on. Okay. A comparison of these catalytic or the specificity constant catalytic efficiency for the same enzyme with the different substrates, or the two different enzymes with the different substrate, is widely used to measure the enzyme catalytic efficiencies. So to know whether which enzyme is more catalytically efficient, so you can calculate either with the same enzyme with different substrate or two different enzymes with different substrate. So this is a possible. This is also possible. So based upon this, you can categorize your enzyme. So first of all, this we have discussed based upon K turnover number of catalytic constant. Catalase is having 4 into 10 to the power 7. Whereas if you calculate this value, this catalytic efficiency or the specificity constant, so you need to divide this value by some value Km, and you will get 4 into 10 to the power 8. So this is more catalytically efficient enzyme. So both are different things. You need not confuse. One is the turnover number, one is catalytic coefficient or efficiency, catalytic efficiency. So these are two different terms you should keep into your mind. One is kcat, one is kcat divided by km. So in today's class, we have discussed the pre-steady state, steady state. There is some assumptions. There is derivation of Michaelis-Menten equation, and this curve. What this curve is showing, it is actually showing the two things. One is initial part is actually the first order rate kinetics, whereas the second part is showing some kind of zero order rate kinetics. So this all we have discussed in today's class. Next, we will also see, because it is not possible to find some values based upon this hyperbolic plot. Therefore, we need some line plots, line equations. Okay, so therefore, we need to switch to some LB plot or hence Wu's plot or some other plots where you will not find a curve, but there is a straight line, and it is easy to find some of the values based upon this straight line because you can easily find the specific values. Okay, but if you look into this is called LB plot, this is Lean Weaver Berg plot. But if you try to find the values, suppose in a Michaelis-Menten curve, that is a hyperbola. So there is no, okay, so let me first reach to this particular curve. So this is the curve. And suppose you need to find the two values, suppose one value here and one value here. So actually these are two different values, but if you try to find it, they will come somewhere here, and also their velocity will remain somewhere here. So there is no much difference. And when the enzyme is saturated, suppose here you took two values, so you can find they are having different substrate concentration, but if you try to find the velocity, you will find they are having the same velocity. Therefore, you are not able to predict appropriately what will be the rate of reaction at these substrate concentrations when the enzyme is saturated with the substrate. Therefore, you will require some additional, more advanced line equations or line plot so that you can easily calculate these values also. Okay, so we will discuss those plots in our next classes, upcoming classes. Hope today whatever is told to you in today's class is clear, and